Hello, everyone, and welcome to this preview of our upcoming sheet metal roll forming cost model. My name is Karen Gold, and I'm a Director of Product Management at aPriori. In the next 25 minutes or so, I'll give you some background about the roll forming manufacturing process, and then I'll demonstrate the cost model in aPriori. This sheet metal roll forming cost model is currently under development, but it's pretty far along, and it will be available for customers in the aPriori 2022 R1 release this spring. Before we begin, just a few housekeeping notes. If you have any questions after you view this demo, I will be in the Cost Insight live meeting room from 2 p.m. to 5 p.m. Eastern Time. Feel free to join to connect with me and other attendees and have your questions answered. If that time block doesn't work for you, or if you prefer to meet one-on-one, you can also schedule time with me via the meeting scheduler. On the event website, near the chat panel, choose People and then select my name, Karen Gold, and schedule a meeting with me. Alternatively, you can use the Request Info button on the main showcase page to have someone reach out to you. We've uploaded a PDF of today's presentation and the recording and other additional resources which you can access through the Files panel. Just a tiny bit of background about me. As I mentioned, I'm a Director of Product Management at aPriori. I've been with our company for 12 years. I have a background in mechanical engineering and CAD/CAM, and I'm just really excited to work here. I'm even more excited than when I started, because we are offering so many wonderful manufacturing cost model applications. And with that, I'm going to turn off my camera so you can concentrate on the slides. Roll forming is one of our most requested cost models. In our enhancement database, we have over 40 requests from 40 different customers to estimate roll form parts. And when you look at this slide, you will see why. Roll forming is used to make parts across all the industries in our customer base. So if you think of the automotive industry, applications include parts like bumpers, door beams, crash tubes, seat rails, exhaust pipes, and decorative trim. Widening that out a little bit more broadly to transportation, roll forming is used for parts like train and truck, exterior roof and side panels, interior framing and stiffening channels. And even a little bit more adjacent to that, crash barriers and guardrails are made with roll forming. In the aerospace industry, roll form parts include things like airframe stringers and interior components like trim and window frames. Jet engine components such as honeycomb seals, shrouds, and backing rings are made with roll forming. In the construction industry, roofing, gutters, door and window framing, shelving, railings, air ducts, and fencing all are made with roll forming. Roll forming actually has a nice little niche in the solar panel power industry. All the solar panel frames and mounting structures are made with roll forming. And last but not least, in consumer products, parts like appliance panels, handles, door seal retainers, decorative trim, and shelving all are made with roll forming. Now, one of the key benefits of the roll forming process is that it can manufacture very high production volumes, and the parts coming off the roll forming line often are fully finished, or at the very least, very near finished after part cutoff. Sometimes a painting or another secondary treatment may be required. Other benefits include a wide range of materials can be roll formed. Almost all materials can be roll formed. It's a low scrap process. It can achieve tight tolerances, produces a very nice surface finish. The tool life generally is long for roll forming die sets. And the process itself can make very long parts. If you think about those train panels and structural members that I mentioned, or guardrails, these can be tens of feet or meters long. Another benefit is that you can achieve cost and weight reduction with roll forming, particularly for parts that formerly were stamped. Roll forming can form higher tensile strength materials like ultra high strength steels than cold stamping can, and it can do it more economically than hot stamping. Now, this slide shows just a kind of high-level overview of the roll forming process itself. Roll forming is a high-speed method of progressively bending coiled strip metal into a uniform cross-section. And so the sheet metal strip does pass through multiple roll dies or roll stations to incrementally form that final cross-section. We show 6 roll or 5 roll stations in this illustration. Typically it requires more rolls than that, but this is sort of conceptual. The actual number of roll die stations does depend on things like the cross-section complexity of the final desired cross-section, the thickness of the material being formed, and also the required tolerance specifications. Roll forming lines can run very fast, up to hundreds of feet per minute, but the overall line speed is limited by the slowest process in the line. That's kind of a nice segue to my next slide here, where I show typical processes included in a roll forming line. So right at the center, we have our roll forming mill. That's the series of roll dies, which incrementally form that desired cross-section profiler. But there's quite a number of processes before or after it in the line. We start with an uncoiler, which feeds the coiled material stock into the line. The stock then passes through a flattener, which removes any bow from the material. The line typically includes at least one punch press to create any holes, cutouts, or embossments in the part. In this illustration, we show just a pre-punch press, meaning that the press is in line before the roll forming mill. Pre-punching is used for parts which have pretty typical or standard tolerance requirements, which allow the holes and features to be punched in the flat strip. But there may be additional punch presses required after the roll forming mill, which we call post-punching, or even between roll dies, which we call mid-punching, if tighter tolerances are specified for the punch features and sort of the accessibility of the geometry requires it. Now, moving along, if the desired cross-section is closed, that can be achieved by using one of several seam welding processes in line to fuse the 2 open edges together. A cutoff press is used to cut the parts to length. And if the part is bent along its length, as opposed to the bends that form that cross-section profile, that sort of profile then can be achieved either by roll dies within the roll forming mill, or it may require a post-cutoff bending process, such as CNC profile bending or rotary draw bending. Just wanted to make a quick mention too that the cutoff press and any mid-punching or post-punching presses use accelerated dies. So the die is actually moving when it punches or cuts the part. Physical limits on how quickly that die can accelerate and what speeds can be attained are one of the main constraints on the overall line speed. Pre-punch presses can also use accelerated dies, but typically they use a stationary die with buffer loops of material on either side of it. That's the preferred approach because the stationary dies can be larger and punch greater numbers of features at once without causing a significant reduction in the line speed. And with that, I'd like to jump over to aPriori Professional and demonstrate this new cost model. Note that the roll forming will be available both in the on-premise and cloud versions of our products in the spring of 2022, but I will be demonstrating it in aPriori Professional today.
Here I have an example of a typical roll-formed part. This part's a structural component for a large hopper or grain tank. And you can see that all I've done now is set the annual volume to 12,000, and I costed it in our new sheet metal roll forming process group. This process group will be licensed separately from our other sheet metal process groups, and it will be available in our next major release, aPriori 2022 R1. So first, let's look at the geometry that aPriori has extracted for this part. It's a sheet metal part, so it does have a blank GCD. That simply represents the outline of the flat metal strip that is formed to make this finished part. And in particular, the width is important here. Next, we also have a cross-section GCD. And you can see the cross section is displayed in the lower right corner of the viewer window. And also you can see it kind of superimposed on the ends of this part. The cross section, of course, shows the profile of the part that is formed from that flat strip. And it also shows or indicates the orientation of the part after it exits the roll forming mill. It's in this kind of catch water orientation. aPriori determines the orientation of that part or cross section so that it will maximize the accessibility of the bends and therefore minimize the size and the complexity of the roll set tooling that's required. aPriori also generally balances the cross section in the case that they're not symmetric, enabling the geometry on each side of the part to be made simultaneously and minimizing the number of passes. Moving on through other GCDs, we have a lot of bend GCDs, and in particular, all these straight bend GCDs. These represent the bends that run the length of the part and are created by passing through the series of roll dies. Now, if the whole part were bent along the length as opposed to the profile after that profile was formed, we would recognize that as a different type of bend GCD. It would be called simply a bend GCD instead of a straight bend. And so aPriori can differentiate between bends that would be made by the roll forming mill versus made subsequently by a CNC profile bending, rotary draw bending, or some other bending process. Other GCDs on the parts are holes. Any cuts through the material are recognized either as simple holes if they're round, or complex holes if they're not round, like the rectangular and oval shaped cutouts we have on this part. If we had any notches that intersected the edges of the blank here, rather than being an enclosed internal cutout, we would extract those as cutout GCDs. All these different types of sort of holes vary in name, but they all can be made by a punching process. Now let's look at the process routing that aPriori has determined in the manufacturing process pane. Just like in the slide I showed earlier, we start with a coil of material stock, which is cut to the width of the part's flattened blank. Then we have an uncoiler process, which feeds that strip into the line. A coil flattener, which is used to correct crossbow in the thicker gauge materials and longitudinal bow in higher strength materials. And it prepares that strip for any pre-punching operations. Next, we have a punch press. In fact, if we drill down a little bit, it's a pre-punching press, and that performs all the punching of holes, cutouts, and other embossments that can be done when the strip is still in the flat state. Next, we have a roll forming mill. In this case, you'll see we have 22 passes or roll die sets, which are required to incrementally form this part. And finally, we have a cutoff press. I'm going to go to this part details tab here. Now, as I've mentioned before, since roll forming involves a continuous coil-fed line, the slowest process in the routing does determine the overall line speed. So we have displayed some custom outputs that indicate the effective line speed and which process determines it. Now, in this case, you'll see that while the roll forming mill itself can support a line speed of over 1,000 millimeters per second, so more than a meter per second, the cutoff press isn't capable of supporting those speeds, and it's the limiting factor in this case. So as a result, the line is running at a reduced speed of 326 millimeters per second, so about a third of what the roll forming mill could support solo. And the cutoff press is indeed the limiting factor. As a result of this adjusted line speed, we calculate the cycle time of the part is 1.87 seconds. Now let's hop over to the part summary tab. And you'll see that initially we've estimated this part as having a piece part cost of $6.46. The tooling contributes another 69 cents or so, if I'm doing my math correctly, and to make a fully burdened cost of $7.15. Material cost is quite dominant, as is typical for sheet metal parts. It's about 77% of the part cost. Tooling costs are about 10% of the cost. Setup costs are about 2.1% of the cost, and labor and overhead are quite low, less than 1%. So let's look a little bit more at this part to understand how aPriori is generating these estimates. Go back to our manufacturing routing here. And first, I really want to talk about the roll forming process logic itself, since that is at the heart of this new cost model. And you'll see that what we do is we group different bends and we assign them to different roll station in the order that the bends are made. Each roll station in this list represents a matched set of roll dies that the part passes through. So if I click on the first roll station here and highlight the GCDs made on that roll station, I can zoom in here and you'll see that it's these 4 bends that comprise the stiffening rib down the center of the part. And it makes sense that that feature is formed first, as we need to draw the material inward toward the center of the part. And in fact, that geometry isn't made by simply passing through one set of roll dies. These are each 90-degree bends. They do need to be formed incrementally. So aPriori has determined that 6 roll stations or series of dies are needed in parallel to form that geometry, with each one bending the material about 15 degrees. And so that's why all these 6 roll stations are highlighted. The geometry here is made incrementally over these 6 stations. So let's now move on to the 7th station. And I can highlight the bend geometry that are made here, and I can zoom out a little bit, and you'll see at this point we begin forming these 2 outermost bends, one on each side of the part. Those are formed next. These bends are about 70 degrees, and aPriori has determined we need 5 roll stations to form those, as opposed to the 6 needed to make the central rib. If we move on to the next set of roll stations, then you next see that we're moving inward. This next pair of bends is made and also require 5 roll stations to make it. And finally, these 2 inner bends are made, essentially folding the wings of this part upward into this almost W kind of shape. So other than the rib feature that we started with, we are working in an outside inward order. And that's done so that the bends are easily accessible and we minimize the size and complexity of the roll set tooling that would be required. Finally, at the end, there's one roll station. You'll see there's no plus sign. That means there's no additional geometry being formed here. It's an idle station. It represents a finishing pass that just sets that final profile. The number of these finishing roll stations that aPriori adds depends on the tolerance requirements for the cross-section profile. By default, aPriori assumes kind of a standard tolerance, which requires a single finishing pass. All right, so that's kind of the logic for the roll forming process itself. Let's look at a couple other things. Let's look at the punching process. Let's look at how the holes are made. Right now, as I mentioned, all the holes are assigned to this pre-punching process. Zoom out a little here. And that means they're all punched in the flat state before the strip passes into the roll forming mill. If no tolerance is explicitly specified for holes and cutouts, aPriori does assume kind of a standard tolerance requirement of plus or minus 30 thousandths of an inch. That's just over 3/4 of a millimeter, and that's achievable by pre-punching. You can change this assumption using this process setup option to set it to a sort of what we consider a medium tolerance, plus or minus 15 thousandths of an inch, or even a tight tolerance, plus or minus 5 thousandths of an inch. And if you invoke those tighter tolerance requirements, This will cause a mid-punching process or even a post-punching process to be added after the roll forming mill. So you could set that for all the punched features on the part as a whole, or you can either set tolerances for individual features individually in aPriori, or even read them from the CAD model if they're specified in the CAD model and you are using aPriori's advanced PMI reader license. So in this case, I'm going to just change the tolerance for one hole, this hole right at the front right here. And I'm going to specify that it has a tolerance requirement of 0.5 millimeters. And what you'll see when I recast this part with that tighter tolerance requirement on the one hole is that we've added a second punch press. And that punch press is a post-punching process, and it has just that one hole with the tighter tolerance requirements on it. The remainder of the holes are still punched in the flat, as we see here, assigned to the pre-punching process. One thing I wanted to comment on is that while pre-punching typically is performed using a stationary die with some extra buffer loops of coil material on either side of it, post-punching dies and the cutoff die both are accelerated dies. They need to be accelerated so that they're moving at the line speed when they contact the part. So we calculate which speeds are achievable given the estimated mass of the punching and cutoff dies and the distance that they have to accelerate, which is the length of the part. So if we hop back over to our part details view and look at some of our outputs, we see that when we increased the or tightened the tolerance on that hole and added the post punch press, it did affect the line speed. That's because the punch press has become the limiting factor when we've calculated how quickly the punch die needs to be accelerated and the distance it has to do it. It ended up further reducing the line speed. So now it's set to about 220 millimeters per second, as opposed to the 326 millimeter seconds that was achievable when there was only a pre-punching process in the line. And as a result, the cycle time of the part has increased. Previously, we had calculated it at 1.87 seconds, but now with the reduced line speed, the per part cycle time is 2.76 seconds. And you'll notice that in addition, batch setup time and costs have gone up because there is another post-punching press in the line. To go on with a little bit more of our logic, process logic here, we have a cutoff press, and aPriori provides two options for the cutoff die. It can be either a scissor style cutoff die, which does not produce a slug, or a blade die that does produce a slug. aPriori has assigned a scissors style cutoff die. In this case, that is because it prefers it when it's possible because it results in better material utilization. But blade dies are assigned when the part and cross-section geometry requires it, such as parts with hem bends or parts where the cross-sectional bends are obscured and can't be adequately supported to prevent crushing by a scissor style die. So if I indicate here, as I mentioned, if we're talking a little bit about material utilization, and I hop back over to my part summary tab, you will see that the material utilization we've calculated is quite high by default. It's over 95%. The scrap comes really from the cutouts in the part. But if I go and I change my my cutoff style press from using a scissor style cutoff to a blade style cutoff and recast the part, then we'll see the blade cutoff is assigned and the material utilization now is calculated at just over 94%. So the additional slug produced by the blade style die is accounted for. Okay. Just a note about tooling costs. As with our other processes that involve hard tooling, we have an investments tab that itemizes all the hard tooling components and their costs, as well as the cost of making some of that tooling. But I think that the best way to review the tooling is through one of our tooling spreadsheet reports. You can just get to those by saying report spreadsheet reports and picking the tooling report. And when you do that, you will get a tooling report like this one. You can see that it details all the tooling for all the inline processes. In particular, for the roll forming tooling, we estimate those costs based on the number of rolls, in this case 22, the size of those rolls, which we determine from the part geometry, and the tooling material, which is 4140 tool steel by default. In addition to the roll forming tooling costs, we also include the estimated tooling costs for all the other inline processes, such as the cutoff press, and in this case, both the pre-punch press and the post-punch press. And finally, I wanted to just take a quick look at one more aspect of our routing, which isn't required for this part, but could be required for other part types. If I expand out the routing, maybe I'll just move this window a little bit to make it a little more visible. We can see that this routing includes the option for integrated welding. So if this part had a closed cross section, I could weld that cross section with either an integrated high frequency induction welding, rotary spot welding, laser welding, or TIG welding, all inline seam welding processes. If this part had a bend along its length, along the trajectory of the part, we also offer post cutoff profile CNC bending processes to support making those types of bends. That concludes what I wanted to show you in the product today.
And finally, as a conclusion, thank you so much for your time today. We really appreciate it. Again, if you have any questions at this time, please feel free to join me in the live meeting booth or contact me by one of the other methods I mentioned earlier. You can also always send an email to the email address that's on the slide now, or to anybody on your aPriori account team, and we'll make sure we get that question answered. I'm going to also invite you, if you haven't yet provided any roll forming parts to assist in our cost model development, but you're interested in doing so, please feel free to reach out to me for the same purposes. Thanks, and have a great day.